Thank you very much and very good afternoon. It's a pleasure to be here and present our findings. So just a brief discussion on the context. COP21 may be a pivotal event for pushing clean energy deployment. And so what could be its effect really on low carbon energy technology innovation if the government commitments will be translated into effective policies? Then obviously we will have an accelerated deployment of low carbon technologies, which will then draw higher investments on innovation. So deployment and innovation could reinforce each other. And then on the sides of COP21, we have seen these two initiatives, as were already mentioned, with Mission Innovation and Breakthrough Energy Coalition, where governments in first instance and then the private sector have committed to increase the R&D investments. So right now, we just have to be hopeful that the commitments will be reflected into effective policy action. So this is our flagship figure that shows essentially the two of the ETP scenarios. In the so-called 6-degree scenario, which is the reference scenario based on policies that are currently implemented. Now, the name is a bit outdated, but because actually the long-term temperature increase will be about 5.4 degrees with if current policies will not change. And we see that there will be a significant increase, as we know, of energy-related CO2 emissions. And to get to 2 degrees, to a long-term temperature increase of 2 degrees, we will need to cut emissions by more than 80% from 2050 levels. So how do we get there? What you see here are the so-called wedges. So it's the shares of each technology in the cumulative emissions reductions from 2013 to 2050. And it's not that they are decided by expert-based judgments per se. They are the output of a cost optimization model. So we don't decide that CCS and nuclear should be there. It's just based on the cost assumptions and historical learning rates. So where does innovation plays out here? In the 2 degrees, we already embed the historical learning rates. So if there is an increase in the cost reduction path of low carbon energy technologies, at the end, it would essentially make the 2-degree scenario more feasible and more sustainable and more economically sustainable. Because still, a 2-degree scenario would entail additional investment cost on globally to accelerate deployment of low carbon technology that perhaps at least in the short to medium term, the market by itself will not take it up. And then there are some promising signs. Now, we have still kept 2013 as the base here for energy RD&D investments from the IEA member countries, because we still have to double check some country data. And so I prefer to use the most reliable of the data series here. And there has been a reversal in public sector RD investments in the early 2000s, but if we look at the absolute numbers, we are still below the peak that was achieved in the early 80s. And also the share of energy RD&D on total RD&D is still below what was again achieved after the peaks following the second oil price shock. So what's the takeout here is, according to our analysis, we are still the volume of RD investments on energy technology is still not consistent with what would be needed to achieve a 2-degree scenario in a cost-effective way. And in terms of policy support, we all know that innovation, accelerating innovation would need some sort of government support, and there is no really optimal mix that can be generalized in all kind of situations. So, but essentially, the right policy instrument would depend obviously by the degree of the maturity of the technology, but we should not forget that innovation should be also supported for commercially mature technologies, often because there is still a very significant cost reduction potential that the private sector by itself, in absent strong policy signals and policy stability, might not take. Just to give you an example on I would say systemic technology like carbon capture and storage, CCS is a case in point where the policy framework needs to provide support to the technology across the different phases of the technology cycle. So the early phase of progression from demonstration to development, and then further on into deployment. We should not forget that CCS has already some cost-effective applications. And then this is taken from our ETP 2015 analysis, where we had a deep dive on the industry sector. So we analyzed what could be the role of innovative processes and technologies for decarbonizing the industry sector, and we saw that these innovative processes would contribute to about 30% of the cumulative carbon emissions reductions in the industry sector. So again, it is important that best available technologies are deployed today so that more cutting-edge work can be performed on the more radical, innovative technologies. And so again, deployment and innovation can reinforce each other into a virtuous cycle. And then we looked obviously at what policy environment could accelerate innovation in the industry sector. And one thing is that that emerged is that public-private partnerships are really crucial, and for that we should not forget that the shale gas revolution and also the success of the cadmium telluride technology for PV system that was achieved in the early 90s in the US. I'm sorry, the cadmium telluride was a bit later, but these two examples essentially these two technologies are the result of public-private partnerships that dated back to the early 80s, where the DOE in the US was strongly supporting private efforts and actively involved with its RD&D labs, sitting together with the industry. And then obviously a robust protection of proprietary knowledge. We know that it's crucial for partnerships among industrial stakeholders. So we should reinforce here that it is, I just give three important prerequisites for the industrial sector to keep innovating is policy stability, and then policy stability, and then policy stability. The industrial sector really need clear and long-term policy signals. And then we also looked at developing and emerging economies, and we see that the ability of emerging economies to innovate is key to making the 2-degree scenario reality. And this can be achieved through different, obviously, solutions, as you see here. But one thing is that international cooperation is really crucial to enable emerging economies to tap into their own innovation potential. I'm not talking only and thinking about this conventional north to south technology transfer, but because there is a lot of south to south technology transfer going on, and right now is also we have cases of south to north technology transfer. Just to give you an example, for Indian biogasifiers that are being deployed in a few OECD countries. And then we, in our ETP 2015, we also looked at China. So we do develop regional 2-degree scenarios for our modeling regions, and when we did for China, it turned out that our 2-degree scenario was the most ambitious one across a family of other scenarios. So we obviously were questioned. This is not really possible, but again, this is a scenario, is not a forecast. It could be possible if the right support to innovation is provided in China. And in fact, this is already happening because there is a large, significant increase in energy, in public energy, R&D funding in China. And we are already seeing the results because this progress can be illustrated by the increase in share of solar power and LED global export from Chinese companies, which the share rose from 10% to 40%, 10% in 2001 to almost 40% in 2014. And this, so you might say were not really cutting-edge technologies, but this has correlated closely with an increase in patent development over the same period. So we have some indication that China is moving up in the technology added value chain. So ultimately, if you match this with the exporting capabilities of Chinese companies, so the result is that a strong push on innovation from China can make not only the Chinese 2-degree scenario possible, but actually even a global 2-degree scenario more cost effective. So before I conclude, we just the message on our work on innovation is that we need to see innovation and not as a linear process, but as an iterative process with feedback loops across the different phases. So this is not just a theoretical exercise, because understanding of all this feedback can in turn improve better policy making, and we have a few concrete cases where this has happened. And last but not least, in ETP 2016, we looked at urban energy systems and their role in fostering national and global low carbon transitions. And we saw that cities can be clean energy innovation hubs because they can allow to experiment and to some emerging technology progress from the demonstration to the deployment case. So this has been the case, for example, for electric vehicles. So in conclusion, basically we are already starting to look at the well below 2-degree scenario. In fact, we had a workshop on Monday. And so the feasibility of a 2-degree scenario or a well below 2-degree scenario with at sustainable, economically sustainable costs will basically depend on our ability to bring more innovative technology into the markets. And in other words, relying on linear technology progress might not get us there. So we even with very generous market pool measures such as feed-in tariffs and so on, we have to be more brave, and governments have to show much more courage in spending in high-risk projects, and they have to create the right enabling policy environment for the private sectors to invest in research and development. So essentially policy action needs to focus more on the longer term horizon, and unfortunately this has not happened, and we know for political economy reasons why, but I mean we have really this challenge needs to be addressed, the political economy one, if we want to really tackle climate change in a cost-effective way. Thank you.
Thank you very much.